research and discovery. Futurists.
The volcanic peaks of Tenerife bathed in early morning light. Light which in just 8 minutes has travelled the 150 million kilometres from the outer reaches of the sun. Viewed from Earth, this ball of plasma looks deceptively simple. Yet many questions remain over the inner workings of our star.
For 400 years, we've been looking intensively at the sun since the invention of telescopes. The sun is the only star on which we can clearly see details that we can't see on the other stars because they're too far away.
The Teide Observatory on the Spanish island of Tenerife is home to an array of solar telescopes. This, the Gregor telescope, has huge mirrors designed to give close-up, high-resolution images of the sun. Meanwhile, the VTT telescope breaks down the sun's light into its component rays. Recently, new techniques are being used not only to observe the outer layers of the sun, but to probe inside.
The sun is constructed a little like an onion with different layers. In the center, you find the core, which is hot enough and dense enough to enable the core fusion process for hydrogen to translate into helium, and out of that, the sun gets its energy.
One of the biggest challenges in solar physics is to peel back the sun's layers. Oscar van der Leeuwen is coordinating a European research project called HELLAS, focused on this emerging science known as helioseismology.
Helioseismology is a method for understanding the inner workings of the sun, and for that we measure the wave movements on the surface of the sun. And there are a lot of wave movements which can be measured on the surface of the sun.
Leading helioseismologist Pere Palais is working with Oscar on the HELLAS initiative. The techniques he helped develop have already revealed some of the sun's inner secrets.
Today we know the speed of the rotation of the interior of the sun, from the surface up to the final 10% at the core. The sun is not rotating as a solid body, as a homogeneous body, but its speed of rotation varies according to depth.
The telescopes used to study the interior of the sun looked rather small when compared to their big mirrored brethren. That's because they observe the sun as a whole and record how it moves and vibrates.
Instruments like this are capable of measuring pulsations, periodical movements in the surface of the sun with as little speed as a few centimeters per second.
These pulsations follow rhythms and cycles. It's often said that helioseismologists listen rather than look at the sun. Here in the German city of Freiburg, voices, footsteps and trams create sound through vibration. HELLAS project scientist Markus Rutt explains how acoustic waves are generated in the sun.
In the external layer, there are very turbulent movements. Hot matter rises from the inside of the sun in granular cells that are cellular structures in which hot material is swelling up, and between these cells, cooler matter sinks back down into the sun. And between upflows and downflows, there's friction with turbulence, and that turbulence resonates sound.
Down in the optics lab, Markus has translated these vibrations into sounds we can hear.
We analyze the pulsations of the sun. These pulsations are sound waves. We can record them and translate them into a range audible to humans. And so the sun sounds like this. Basically, each star is its own unique musical instrument. Every star has its own sound, and from these sounds we can draw conclusions about the star's inner structure and its age. And here I've got the sound of a star in its terminal phase. It's a red giant. The Sun will eventually become one too, and this star has a much lower pitch and sounds much lower. At the end of its development, the Sun will be a white dwarf. And even white dwarfs have a resonance, and we can also record these waves. So this is the sound of a white dwarf that we analysed.
So we can understand a great deal about the Sun by effectively listening to the acoustic pressure waves running through it. They reveal a profoundly complex body with many layers and zones.
We know
that the Sun is rotating approximately once a month around its axis. But the outer layers of the Sun are rotating at different speeds. And we think that this shearing may be one of the origins of the magnetic cycles. That means the sunspots that come and go every 11 years.
The different layers rotating at different speeds create what's known as the solar dynamo. Pere Payet has pinpointed an area for further investigation.
It's interesting to note this red zone that was a total surprise in the structure of the Sun. Today we've been able to measure its size and also the importance that it may have as the place where the 11-year magnetic cycle is generated.
Understanding the magnetic cycle is the key to fully understanding the Sun and its effect on Earth. But we're not there yet.
I think that the main mystery today is how magnetic activity is generated, how it evolves, and also our capacity to predict it. I think that is the big open question about the Sun, because the functioning of the Sun is governed by that.